Hello again. In this video, we're going to begin talking about the material from section 4.6, which is about linear approximation and differentials. So let's talk about linear approximation first. So here's the idea behind linear approximation. It's always easier to work with linear functions than it is to work with nonlinear functions. So let's suppose we have a nonlinear function whose graph looks like this. And then let's pick some point on that function, say this point here, point P. Now notice as I zoom in on this particular point, the graph of the function starts to look more and more like a straight line. And so for points near this point P, we can approximate the function as if it were a straight line. Okay, so the question is, what line are we going to use to make that approximation? And the obvious answer is we're going to use the tangent line at this particular point P. Notice that the more we zoom in on P, more and more the function begins to look like that tangent line at the point P. Okay, so we're going to come up with the equation of that tangent line, and we're going to use that to approximate the function for points near P. Now, we do have to satisfy one condition before we can actually do this linear approximation. This does not work for every function and every point on functions. So here's a particular function that comes to this sharp point. At this particular point Q, we cannot approximate it as if it were a straight line, because no matter how much you zoom in on the point Q, it doesn't look like a line. It still looks like a V. Okay, so the thing that we're lacking at this particular point is differentiability. Okay, but as long as we have differentiability at the point, then we can zoom in on it and it's going to look more and more like a straight line. Okay, so having said that, let's come up with the linear approximation formula that we're going to use. Okay, so let's just say you have the graph of some function that looks like this, right? It's a nonlinear function, and we want to approximate it as if it were a straight line at this particular point A. Now notice it is differentiable at A, so if I zoom in on this particular point, the function does begin to look more and more like a straight line. Okay, and so what we're going to do is we're going to approximate the function at this particular point as if it were the tangent line at this particular point. So let's come up with the equation of the tangent line at this particular point. Okay, well, we do know a point on this tangent line. It's at A, comma, f of A. And we know the slope of the tangent line because the slope of the tangent line is the derivative evaluated at A. And so we know a point and we know the slope of the line, right? We know a point on the line, we know the slope of the line, and so we can use the point slope formula to find the equation of the line. And remember, the point slope formula says y minus y1 is equal to m times x minus x1. And notice here, x1 is A, and y1 is f of A. So this is x minus x1, x1 is A, and this is y minus y1, and y1 is f of A. Then the slope is the derivative evaluated at A, so f prime of A. Okay, so using the point slope formula, we can come up with the equation of this tangent line. It's equal to this. And if you solve for y, you would just add f of A to the other side, and we get this. Now we're going to think of this as a function, because it really is. A is actually a fixed point. It's the point at which we're trying to find the tangent line. And that means that this is a function of x only. Okay? And so instead of calling it y, the output y, we're going to call it L for linearization. and it's a function of x. Okay, so L of x is equal to f of a plus f prime of a times x minus a. That's going to give us this particular tangent line here. So for any particular point close to a, called x, we can plug it into this formula. That'll give us the y value on the tangent line at this particular point x, right? And we're calling that y value L of x. So that's L of x right there. Notice that L of x is close to f of x as long as you don't go too far away from a. This x value, as long as this x value is close to a, then L of x, which is right here, is approximately the same as f of x, which is right there. Okay, so f of x is approximately L of x, and that's our linear approximation for the function. Okay, so let me do an example to show you how this works. By the way, I already mentioned this before, but let's just go over it again. You need f to be differentiable on the interval I that contains the point a. So suppose f is differentiable on an interval I containing the point a. You need that condition first. Then the linear approximation to the function at a is this linear function, L of x, which is f of a plus f prime of a times x minus a for all x values in the interval I. Okay, so let's do an example where we actually use this linear approximation. Okay, so what we're going to do is we're going to take this function f of x equal to the square root of x. We're going to find a linear approximation to that function at x is equal to 1. Then we're going to use that linear approximation formula to approximate the square root of 1.1. Now notice the graph of this function is nonlinear. Right? The square root of x is a nonlinear function. It actually looks like this. Okay, and so what we're going to do is we're going to take this point x is equal to 1, and we're going to zoom in on it. And notice it's differentiable at that point. So if we zoom in on it, it's going to start to look more and more like a straight line. Okay, and so we're going to find the equation of the tangent line at x is equal to 1. Okay, which is where the linearization formula comes from. So L of x is f of a plus f prime at a times x minus a. Okay, in this case, a is equal to 1. That's the point we're zooming in on. Okay, so this is going to be f of 1 plus f prime at 1 times x minus 1. Okay, so what's f of 1? Well, f of 1, you plug a 1 into here, square root of 1 gives you 1, right? So that's just 1. All right, now we need f prime of 1. Okay, so f of x is the square root of x, and I'm going to write that as x to the 1/2 power. Remember, that's the same as square root of x. Then we're going to find the derivative of that. Using the power rule, you can pull the 1/2 down, and then subtract 1 from the power. So it's going to be x to the negative 1/2. Then we're going to evaluate this at 1. So we need f prime of 1. And when you plug a 1 into here, well, this is actually, since this is a negative, you can write this as 1 over. So first of all, you have a 1/2 in front. Then this is 1 over x to the positive 1/2 power. That's what the minus sign does. Then that's just square root of x. Okay, now if you plug a 1 into here, right, evaluate this derivative at 1, notice that you get 1/2. And that's really the slope of this tangent line right here. Then notice this point right here is 1, 1. Right? That's the point that we know on this particular tangent line, and that's why we're plugging a 1 in here and a 1 in here. Okay, so that's our linear approximation formula, which is really just the y value of for this tangent line. Right? For any particular x value that we pick, this is going to give us the y value on the tangent line, which is approximately the y value on the function, as long as we're near a is equal to 1. Okay, now, so the second part of this problem is let's approximate the square root of 1.1 using our linear approximation formula. Okay, now we're going to compare this to the actual value on a calculator. So the square root of 1.1 is equal to something, and we're trying to approximate that. Okay, so here's 1.1. Okay, the square root of 1.1 would be the y value right here. And we're approximating that by looking at the y value on the tangent line, which is just a little bit above that right there. Okay, that's L of 1.1, that top one. Okay, so we're just going to plug a 1.1 in for this x value and see what we get for our linear approximation. So L of 1.1. Okay, so we get 1 plus 1/2 of 0.1, which is 0.05. So it's 1.05, and that's approximately the same as the square root of 1.1. Okay, so let's actually see what the square root of 1.1 is and see how good our approximation is. Okay, so square root of 1.1 is 1.0488088848. So that's pretty close, right? Our approximation is 1.05. And that's because this point, 1.1, is not that far away from our a value, which is 1. Now, the further you get away, the worse the approximation is going to be. As long as you pick points near a, in this case 1, this is going to be a fairly good approximation. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.